Hi, in this video, we would be discussing what you mean by radial acceleration and centripetal acceleration. Now, we have already studied uniform circular motion is an accelerated motion because even though the speed of uniform circular motion is the same, if you remember the previous video, I had explained to you that the vehicle moving with uniform circular motion has a speed same, let's say 16 kilometers per hour, but the direction of uniform circular motion kept on changing. Therefore, we said uniform circular motion is accelerated motion. Now, this acceleration which we talked about, which changes the direction of of a body moving with in uniform circular motion, is called radial acceleration. So what is a radial acceleration? It's the acceleration which changes the direction of a body moving in a circular motion with uniform speed. So let us understand this in more detail, or consider a circular path rather with an object with the center shown in green. So this is a circular path with the center shown in green. Now the object or the car is currently at this point. There is a force which is applied by a man. Now in this case, whenever you apply a force to a stationary object, now can you see the force is applied in the upward direction? So this force which is applied in the upward direction will make this object move in the upward direction. So this object is expected to move in the upward direction when the force is applied by the man. Now you can think of this force as pressing the accelerator of the car. So you are a man who is sitting inside a car. So you are pressing the accelerator of the car. Now, because of that, you would expect the car to move forward because you have not changed the direction of the steering wheel. So, you have not changed the direction of the steering wheel, you are just pressing the accelerator. So, you would expect the car to move in the forward direction. But now, the object has changed its direction, an object has moved here. Now, this is possible only when there is a force which is acting on the object along the center. So this object, when you pressed force or when you press the accelerator, was expected to move in the straight line. The fact that the object has changed its direction, is due to obviously a force which is acting on this object and it is directed towards the center. If this force which I have shown in green would have not been there, the object would have gone in a straight line. So object is changing its direction only due to a force which is acting on the object and it is directed along the center. Now this force which is acting on the object and it has forced the object to change its direction and it is acting on a line towards the center, or I would say this force is acting towards the center. This force is called as the centripetal force. So centripetal force is that force which is acting on the object. It is in the direction of the center and it is forcing the object to change its direction. I again repeat three important points. This force is acting on the object. This force is directed at the center and this force is called as the centripetal force. Now let's say you have again an object here. At this point, when your car is at this point, you again press the accelerator. So when you press the accelerator, you would again expect the object to move in a straight line. So when you press the accelerator, you would again expect the object to move in a straight line, but the object has changed its direction. Now again, this is possible only when there is a force which is acting on this object and it is directed towards the center. The force which is acting on the object and it is directed towards the center is called as the centripetal force. We know the formula of force as mass into acceleration. So obviously whenever there is a force, there will be an acceleration associated with it. And this acceleration is called as the radial acceleration. So the acceleration which is associated with the centripetal force is called as the radial acceleration, or it is called as the centripetal acceleration. Now this force is only going to change the direction of the motion. It is not going to change the speed of the object. What I mean by this statement is the object is moving at a constant speed, say 20 kilometers per hour. So this object will keep moving with the constant speed of 20 kilometers per hour. The centripetal force will only change the direction of the motion. So the acceleration associated with centripetal force is called as radial acceleration or centripetal acceleration. So radial acceleration or centripetal acceleration will not change the speed of the object, will rather only change the direction of the motion. And centripetal force can be thought of as the force that causes the object to move in a circular path. Or I would say it's a force that causes circular motion. So centripetal force can be thought of as a force that causes circular motion. It only changes the direction of the object. It does not change the speed of the object. It acts on the object, but it is directed towards the center. These are the three important points for you to remember. We would be discussing revising the triangle's law of vector addition. So basically this law is used to add two vectors graphically. Now just a small recap, a vector is represented by using 2 points. One point here, which is the starting point, and one point is the ending point. The starting point is called as the tail and the ending point is called as the head. Now to understand triangle's law, we will consider two velocity vectors graphically. So the first velocity vector is VA bar, which is pointing in the upwards direction. The other velocity vector is VB bar, which is pointing in the rightwards direction. So you have to represent these two as the sides of a triangle. So how do you represent these two vectors as a sides of a triangle? And you have to arrange them in tail head pattern. Now what I mean by this is your tail, this is your head. So let us see the first arrangement of VB, where this is your tail and this is your head. The next arrangement is also going to be in the same pattern. Which pattern? Tail head. So even my VA, now I am moving my VA from here to here. It's in that tail head pattern. So this is your tail, this is your head. So again this becomes a tail head pattern, which is VA bar. Now you will join the tail of the first. Now this point is nothing but the tail of the first, and you will join this with the head of the second. This point is nothing but the head of the second. So when you join this, you get a resultant of two vectors. So this resultant is basically the addition of these two velocities. So when I add two vectors graphically, I will get an answer. The way I add in algebra, 3 plus 4, I get 7. So if I add two velocities graphically, I get an answer. That answer is called as resultant of two vectors. So the steps were very clear. I had to arrange them as the sides of a triangle in a tail head fashion. Tail head. Then I have to join the tail of the first with the head of the second. We will do the derivation of radial acceleration. So we have already understood what you mean by radial acceleration. So now we will derive the formula for this. Now there are two methods to derive this formula. The first method is called as the vector method, which I'm going to discuss right now. And in the next video, I would be discussing another method to derive the same formula. That's called the calculus method. So let's understand this. This is a circular path. This is a body A, which is going to perform circular motion. A is the initial position of the particle. The particle moves to point B. This is the final position of the particle. The particle has moved from A to B in a small time delta t. Now, this AP bar, which I have shown here, is the tangential linear velocity. When we understood radial acceleration, I told you, had there been no centripetal force which forced this object to change its direction, had there been no centripetal force which forced the object to change its direction, the velocity would have been linear and not angular, right? Linear basically means in a straight line. Therefore, the object would have moved in a straight line, and therefore we represent a velocity, or I would say, therefore we represent a linear velocity as tangential. So AP bar, remember, AP bar is a tangential linear velocity at A. Similarly, when I draw a tangent at B, BQ bar is a tangential linear velocity at B. So what is BQ bar? It's a tangential linear velocity at B. Now, the direction of velocity is changing. Can you see this? AP bar at point A was directed towards the north, and BQ bar at point B, it's directed towards the northwest. So this is the north upwards, this is the west on the left. So this BQ bar is directed towards the northwest. Therefore, I say direction of velocity is changing. And we know whenever direction of velocity is changing, we say the motion is accelerated. And this acceleration is basically called as a centripetal acceleration or radial acceleration. Now understand the next derivation. Now AP bar is the velocity vector, linear velocity vector at A, and we know from basics of vectors that we can displace this vector AP bar and I can move it parallel to itself. When I say move it parallel to itself, I'm not going to change its direction. I am just going to move this AP bar to this point B. So when I move this AP bar to this point B, I get BR bar. Now BR bar is nothing but it's the same vector AP bar. I have just moved the vector AP bar to a new point BR bar. So I have displaced AP bar parallel to itself. So I write AP bar is parallel to BR bar. So now we are supposed to join your RQ bar. Can you see this is R, this is Q. So now we are going to join the RQ bar. So this is what I have joined the tail, or I've joined the head of R to the head of Q. Now why do I do so? Why I use this direction? It's very simple. I can make you visualize this, that this is your tail head. This is your tail head. If you remember your triangle law, this was your tail head, this was your tail head. So you had to arrange the two vectors in the tail head fashion and join the tail of the first vector to the head of the second vector to form a triangle, right? So this is your tail head, this is your tail head, and I'm joining the tail of the first vector to the head of the second vector. So therefore, by triangle law, I can say this BR bar plus RQ bar. So this is your BR bar plus RQ bar is equal to your resultant. Your resultant here is BQ bar. So again, I repeat, this is tail head and tail head. So these are the two vectors, and I am finding out the resultant by joining the tail of the first vector with the head of the second vector. So I get a BR bar plus RQ bar is equal to BQ bar, which is your triangle law. Now, if I take this BR on that side, if I take this BR bar on that side, I will get an RQ as it is RQ bar, BQ bar as it is. This BR bar goes on that side, becomes minus BR bar. Now why I am doing so? I am interested in calculating RQ bar, and RQ bar is going to be this RQ bar, right? Because this is actually the resultant. which I want. Now, why do I want RQ bar? Let us understand this. If you remember in the previous slide, I had told you AP bar is a velocity vector at point A. So AP bar is just moved to another point BR bar. And your BQ bar is a velocity vector at point B. So there were two tangents. The tangent at A was AP bar, which was just moved above here to BR bar. And the tangent at B was BQ bar. And we know this tangent represents velocities, and we need to find out RQ bar, which is the resultant of this velocity. Right? This RQ bar becomes resultant of this velocity BR bar, which is the velocity at A, and the velocity BQ bar, which is the velocity at B. So you have an RQ bar is equal to BQ bar minus BR bar. Now if you carefully understand, this BR bar is equal to AP bar. Why? Because they are parallel, and parallel means, first of all, when two vectors are parallel, it means the direction is the same, and my AP bar is equal to BR bar. So instead of this BR bar, I am going to substitute AP bar. Now let us understand what this triangle law means. I already told you AP bar is a velocity at point A. So AP bar is velocity at point A. BQ is a tangent at point B, so it is a velocity at point B. So AP is a velocity at point A, BQ is a velocity at point B, and RQ is the resultant velocity. So I write this BQ as velocity at point B. Can you see this BQ is tangent at point B? So this is the velocity at point B. AP is the tangent at point A, so it is the velocity at point A. And RQ bar is basically the resultant of these two velocities. So this RQ bar is basically called as delta V, which is nothing but change in velocity. So what is your RQ bar? It's nothing but delta V, which is nothing but change in velocity. Now understand this, that this A and this B, I'm joining it to the center. So when I join this A to the center and I join this B to the center, I get two radiuses. OA is the first radius, OB is the second radius, and this angle at the center is called as delta theta. So I get two radiuses, OA and OB, and the angle at the center is called as delta theta. Now let's take this triangle out. So I take OA and OB outside. Remember, the angle between the two is called as delta theta, and that delta theta is the angle between the two radiuses. So therefore I am saying OA and OB are the radiuses. Delta theta is the angle. Now understand, I have a QB bar. Now can I say QB bar was a tangent at point B? QB bar, or I could say BQ bar. Carefully see the arrow movement up. The BQ bar is the tangent at point B. And I know one important property from geometry, that a tangent and the radius, the angle between a tangent and the radius is 90 degrees. So two things for you to, is very important for you to remember, that your OB bar is your radius, BQ bar is your tangent. So I'm moving this tangent down. That's the first thing you need to remember. Again say, I'm moving this BQ bar down. So can you see I've drawn OA bar and OB bar outside? Now I am going to move this BQ bar down. So I move this BQ bar or QB bar down. But remember, this QB bar is basically a tangent at B. Now this is a tangent at B, and I know one important property, that OB is the radius, QB is the tangent, and angle between the radius and the tangent is 90 degrees. So I am going to mark this as 90 degree. This is the angle between the radius and the tangent, and it is 90 degrees. Now, if I call the third angle alpha, I know sum of the angles of a triangle equal to 180, right? So if I remove 90 from 180, my angle, this 90 degree plus delta theta plus alpha, 90 degree plus delta theta plus alpha would have given me 180 degrees. So if I remove this 90 degrees, I can say this alpha plus delta theta is nothing but 90 degrees, right? Because 90 plus this 90 gives you 180, which is the sum of the angles of a triangle. So in this triangle, I am saying alpha plus delta theta is equal to 90 degrees. Now, understand one important thing. Can you see this AP bar? Now, this AP bar was a tangent at point A. Carefully see this. Huh? This AP bar was nothing but a tangent at point A. So now I draw this AP bar here. This is a tangent at point A. Again, this OA bar is the radius. So this OA bar from this diagram is the radius. AP bar is the tangent. So let's say I call this angle here. Can you carefully see the arrow? I call this angle here as beta. So I am calling this angle here at beta. I know AP bar is a tangent at A. OA bar is the radius. So I know AP bar is the tangent at A, OA bar is the radius. So I know the angle between a radius and a tangent is 90 degrees. So angle between the radius OA bar and the tangent AP bar is 90 degrees. Therefore, I will say alpha plus beta is equal to 90 degrees. Now, when you compare these two equations, the first equation says alpha plus delta theta is equal to 90 degrees. The second equation says alpha plus beta is equal to 90 degrees. So from this, obviously, can I say my beta is equal to my delta theta? Because this alpha can get cancelled, this 90 can get cancelled. So obviously, my delta theta will be equal to beta. Because from this equation, let's imagine alpha to be a number. So when I say that, I say 40 plus 50 is equal to 90. So if this is the alpha 40 out here, this alpha should also be 40, right? So this is again 40 plus 50 is equal to 90. So you get delta theta, which is nothing but beta, right? So this delta theta and this beta are both of them 50 in our example. So this beta turns out to be delta theta. Now we need to figure out where is this beta in this diagram. Now what is beta? Beta is the angle between two tangents. Remember carefully. Huh? This tangent AP bar is the tangent at A. This tangent QB bar, this red one is a tangent at QB bar. So it's a tangent at B. So the angle between these two tangents was called as beta. So here, if you remember, I had displaced my AP bar to BR bar, which basically means I had moved my AP bar to a new point BR bar. So this AP bar and BR bar both are equal. BR bar is a tangent at A. QB bar is a tangent at B, and the angle between the tangent is called as what? Beta. So I will say this is beta, which is the angle between the two tangents, and this is nothing but delta theta. Because I just proved beta is equal to delta theta. Now, in this diagram, just imagine B to be the center. If you imagine B as the center and then you draw a circle. So you imagine B to be your center and now you are drawing a circle. So let's say I draw a circle. So when I do that, I suppose you know your circle is this, your angular displacement is delta theta. So as per the formula for angular displacement, we had studied this in the previous videos, angular displacement is equal to length of the arc upon radius. So this is my center. This is that arc, right? The RQ bar is that arc. And my radius is nothing but either BR bar or BQ bar. I repeat, this BR bar or this BQ bar is your radius if B is the center, and your RQ bar is the arc. So as per the formula for angular displacement, which is equal to length of the arc upon radius, I would write delta theta is equal to length of the arc. The length of the arc in this case is RQ bar. Upon the radius in this case I have considered is BR bar. Now we already know this from the previous slide that we had proved RQ bar is equal to BQ bar minus AP bar, and that RQ bar was the resultant, that is change in velocity delta V. So instead of this RQ bar, I can write delta V. So instead of this r q bar, I would be writing delta v. Now br bar, if you remember, is the velocity at point A. So the velocity at point A was moved upwards. That velocity which was moved upwards was called as br bar. So this br bar is nothing but the velocity at point A. So this br bar is going to be called as a velocity vector which is parallel to the velocity at point A. So br bar is a velocity vector which is parallel to the velocity at point A. So instead of br bar, I will put velocity v. So I get an equation here. If I substitute, I say delta theta is equal to delta v by v. So if I want the value of delta v, I multiply this v with delta theta. So when I multiply the velocity with delta theta, I get the change in velocity. So the change in velocity is equal to velocity multiplied by delta theta. Delta theta is basically an infinitesimal or instantaneous angular displacement. Now, we know this from the previous slide, and we know r q bar is delta v, and we know delta v is equal to v times delta theta. Now acceleration formula is change in velocity upon time. Now this is a formula for acceleration. If I am interested in finding out instantaneous acceleration, listen to this carefully. If I am interested in finding out instantaneous acceleration from the fundamental videos, I know we need to apply limits to find out instantaneous acceleration. So you take this acceleration would be called as change in velocity delta v upon time delta t, because change in velocity, this change is represented by delta, and time is represented by change in time is represented by delta t. Delta basically means change, v basically means velocity. So time here means t and delta means what? Change. So to this acceleration, now we are going to apply limits. Now why we are applying limits? Delta t tends to 0 because we are talking about instantaneous accelerations. From the fundamental videos, I had made it very clear, instantaneous acceleration, you have to apply limits. So I get limit delta t tending to 0, which gives me delta v upon delta t. So delta v upon delta t was my acceleration, right? Delta v upon delta t was my acceleration, to which I have applied limits. So I have limit delta t tends to 0, delta v by delta t. Now instead of this delta v, I can substitute v delta theta. So instead of this delta v, I am going to substitute v delta theta. So I write limit delta t tends to 0. Instead of delta v, I substitute v delta theta by delta t. Very clear? Now understand one important thing, that my velocity is constant in uniform circular motion. Right? Why my velocity is constant? I told you the acceleration is going to only change. The direction of the velocity, the magnitude of the velocity will remain constant. So I say velocity is constant, so this velocity can be taken outside. So when I take this velocity outside in the formula for acceleration, I write velocity outside, then I write my limit delta t tends to 0, delta theta upon delta t. I write my velocity outside, then I write limit delta t tends to 0, delta theta upon delta t. Now what is delta theta? Can I say delta theta is change in angular displacement? What is delta t? Time. Change in angular displacement upon time is basically called as angular velocity omega. So if you remember the fundamental videos, I told you change in angular displacement upon time is nothing but angular velocity, which is called as omega. So the first formula for centripetal or radial acceleration is A is equal to velocity, or I would say linear velocity, multiplied by angular velocity. So A is equal to v omega. Your radial acceleration is equal to velocity multiplied by angular velocity. That's your first formula. So you take this first formula. We have already studied this formula, v is equal to r omega. Remember, this is a relationship between linear velocity and angular velocity. So instead of this v, I can substitute r omega. So when I do that, I write instead of v r omega. This omega is going to be written as it is. Now omega into omega gives you omega square. So I will get acceleration is equal to r omega square. This is your acceleration, which is equal to r times omega square. Another formula for radial acceleration. Now again use the same formula. V is equal to r omega. From this I can take this r down and I can say V by r is equal to omega. So instead of this omega I can substitute what? V by r. So in this r I am going to keep as it is. Instead of this omega I would be writing V by r. So I would be writing V by r the whole square. So when I solve this, I will write this r as it is. I will write this as v square by r square. One r will get cancelled. So if one r gets cancelled here, I get v square by r. So acceleration is equal to v square by r. This is my third formula for centripetal or radial acceleration. Now, understand one important point. I'm going to focus on what is the direction of this acceleration now. This is a diagram which I have taken from the previous slide, and I know delta V is RQ1. Change in velocity is RQ. The formula for acceleration is change in velocity upon time. So wherever this RQ is going to point, that is the direction where my acceleration will point. I again repeat, acceleration is change in velocity upon time. Change in velocity is delta V, which in this diagram was RQ bar. So wherever my RQ bar is pointing, that is the point where my acceleration is going to point, because the formula for acceleration is change in velocity upon time. So wherever my RQ bar is pointing, that is a point where my acceleration is going to point. So let's do this. Let's make the distance between A and B very small. Now this distance between A and B in this diagram is large. So I'll draw a new diagram where I'm going to make the distance between A and B very small. So when I take this circle, I make the distance between A and B very small. Now this at A I'm drawing a tangent, which in this case was AP. Yeah? So at A I have drawn a tangent AP. At B also I will draw a tangent. Now then if you remember, I told you I displaced this tangent AP bar to a new point BR bar. So now also I will take this tangent from here and move it to this point. Remember, I will take this tangent from here and move it to this point. So now I have taken this tangent and I have moved it to this point. Now this is going to be my resultant, right? So I draw this resultant. This resultant is RQ bar. Can I say this resultant is change in velocity? And this resultant is pointing towards the center of the circle. This resultant was change in velocity. That is something which I know. But this resultant is now pointing at the center of the circle. Now, since this resultant is pointing at the center of the circle, listen to this carefully. Since this resultant is pointing at the center of the circle, my acceleration, which is change in velocity upon time. So if my change in velocity is pointing at the center of the circle, my acceleration will also point at the center of the circle. Since my change in velocity is pointing at the center of the circle, my acceleration is also going to point at the center of the circle. So I am going to say the direction of radial acceleration or centripetal acceleration is towards the center. Next, in vector form, understand one thing: anything which is directed away from the center. If you remember, this was a radius vector which I had discussed initially. This is directed away from the center. So in circular motion, anything which is directed away from the center is taken as positive. And anything which is directed towards the center, for example, the centripetal acceleration was directed towards the center, it's taken as negative. So we write the formula of centripetal acceleration which we derived in vector form. So I'll write A bar is equal to minus omega square into r. Now this minus represents that it is directed towards the center of the circle. What this minus represents, it's directed towards the center of the circle. Now we'll understand certain basic formulas. We just have a last modification of the formula for acceleration. Now we know this basic formula: speed is equal to distance upon time. So in circular motion, can I say my speed is v? So distance covered is the circumference of the circle, and this circumference of the circle is 2 pi r. My time period is t. So my v is equal to 2 pi r upon t in circular motion. Now I know a formula of acceleration as v square upon r, and I know the formula for v as 2 pi r upon t. So I can write this v square upon r as v square divided by r. Instead of this v square, I can substitute 2 pi r upon t. So instead of this v square, I'm going to substitute 2 pi r upon t. When I do that, I am substituting, instead of v, I'm writing 2 pi r by t the whole square divided by r. Now if I solve this, 2 square is 4. Pi square is going to be pi square. So I'm going to write here pi square. Now r square is going to be written as r square. So I have 4 pi square r square by t square divided by r. So when I am converting a division into multiplication, I take the reciprocal. So this r is going to cancel out with 1 r here, and I get the formula as 4 pi square r by t square. So this is another formula for acceleration. The last formula is centripetal acceleration is 4 pi square r by t square.